Good morning, students. Welcome to your chemistry class. Let us further discuss the chapter Chemical Bonding and Molecular Structure. The objectives of our today's topic will be valence shell electron pair repulsion theory, and in this we are going to cover its main postulates, steps involved in predicting the shapes of molecules, applications and examples of VSEPR theory. So to understand valence shell electron pair repulsion theory, let us first know that which scientists first gave this theory. So Sedgwick and Powell in 1940 first proposed VSEPR theory in order to predict the geometry or shape of a covalent molecule. Later, the further developments were done by Nhalom and Gillespie in 1957. Now, what are the main postulates of VSEPR theory? The first one is the shape of a molecule depends upon the number of valence shell electron pairs present around the central atom. Supposing the central atom is boron, we know that the valence electrons present in boron is 3 because the atomic number of boron is 5. Similarly, the valence shell of chlorine consists of 7 electrons and that of oxygen consists of 6 electrons. Pairs of electrons in the valence shell repel one another. We know that because they are negatively charged, so there the repulsion will be there. Now the next point is the position of the electron pairs in space around central atom are such that there is minimum repulsion and maximum distance between the atoms. So the electrons arrange themselves in such a way so there is minimum repulsion and maximum distance between the atoms, and the magnitude of different types of electronic repulsions follow the order given below, that is lone pair repulsions are more as compared to lone pair bond pair repulsions, and bond pair repulsions are the least. The electronic repulsion between two pairs of electrons will be minimum if they are as far apart as possible. So in a molecule, the atom arranges itself in such a way that the repulsions are being minimized and the distance between them is maximum. So as you can see, these are supposing the bond pairs. So these bond pairs tend to move closer due to greater repulsion exerted by the lone pair. So this is a lone pair. Lone pair repulsion is greater as compared to lone pair and bond pair. The next postulate is the shape of a molecule can be predicted from the number and type of valence shell electron pairs around the central atom. Okay, so first we have to count the number of electron pairs present around the central atom, and second is when the valence shell of central atom contains only bond pairs. So supposing there are only bond pairs, the molecule assumes symmetrical geometry due to even repulsions between them, like trigonal planar, since the atoms are all same and there are only bond pairs present. So therefore the example is BF3. In this no lone pair is present, so therefore even repulsions are there between the atoms. However, the symmetry is distorted when there are also lone pairs along with bond pairs due to uneven repulsion forces. So therefore, as you can see here in the diagram, ammonia molecule is there. So there are 3 bonds between nitrogen and hydrogen, but there is one lone pair also present, due to which the trigonal planar structure of the ammonia is not possible, due to which the angle is different from the regular tetrahedron angle, that is 109 degrees, and here in ammonia 107.5 degree angle is observed because of 3 bond pairs and 1 lone pair. Now, what are the steps involved in the prediction of geometry of molecules? So if there are number of molecules given to us, then how we are going to predict that what should be the geometry or shape of the molecule? The first one is that we should know which one is the central atom. Then draw the electron dot structure of that central atom. That means the atom with its valence electrons. Now, if it is BF3, 3 atoms of fluorine is attached to boron. That means boron is the central atom here. We have to write the electronic configuration of both boron and fluorine. And when we write the valence electrons of boron and then of fluorine. So there are total of 3 pairs of bond pairs present in the structure BF3. Next, we have to find the arrangement of electron pairs. Then find arrangement of bond pairs, as we have already discussed that in the structure BF3 there are 3 bond pairs. Determine the geometry based on number of bond pairs and lone pairs of electrons. So in this case only bond pairs are present, but in some cases lone pair can also be present. The pair of electron that is not taking part in the bond formation can also be present. So on the basis of the two, we have to determine the geometry of the molecule. Now this chart depicts that if there are no lone pairs present, then what will be the geometry? If one lone pair is present, then what? Then two are present, then what will be the geometry accordingly? Now for a structure of AB2 type, that means there are two atoms attached to the central atom. If they are having no lone pairs in them, so the geometry will be linear. Similarly, trigonal planar will be for one central atom connected with three other atoms. But if in that, if one lone pair is present, then the geometry will be bent. Now, if there is one central atom connected to four different atoms, and if there are four bond pairs, that means the geometry will be tetrahedral. But in that bond pairs, if there are three bond pairs and one lone pair, then it is trigonal pyramidal. And if there are two lone pairs in the same case, then the geometry become bent. Then trigonal bipyramidal will be same. If no lone pairs are present, then this will be the structure. If one lone pair is present, then the shape becomes sawhorse. And if there are two lone pairs present, then the shape is T-shaped structure. And if there are three lone pairs present, then the shape will be linear. If supposing there is one central atom and six atoms connected to the central metal atom, that means there are total of 6 bond pairs, then the geometry will be octahedral geometry. And if one of those is having a lone pair, that means it will be square pyramidal. If two lone pairs are present, that means square planar. And if three are present, T-shaped. And if four lone pairs are present, then it means that it is linear. So two bond pairs and four lone pairs means the geometry will be a linear geometry. Now let us see some examples based on geometries of VSEPR theory. Now in this case, same thing is depicted, but along with it, we have given types and examples. So here, two structural pairs, that means one central atom with angle, it will be having 180 degree. It is AX2 type, that means there is one central atom and two atoms are attached to that central atom. The example of such thing is BF2. Now if there are three bond pairs, it's BF3 as an example, and the geometry is trigonal planar. The angle is 120 degree. If there is one central atom connected to four different atoms, that means it is a tetrahedral geometry. That means the angle here will be 109.5 degrees. And the example of this will be CF4, CH4, etc. Then if you have trigonal bipyramidal geometry, you can see the geometry. Now there are two types of angles present here. One is 90 degree. It's between the axial and the equatorial ones. And between the equatorial one, the angle is 120 degree. So they are 120 degree apart from each other. The example of such molecule is PF5. We can also say PCl5 and so on. Then if you have 6 bond pairs and it's octahedral geometry and the angle between the octahedral geometry is 90 degree, the example of such molecule is SF6. Now if you have supposing tetrahedral geometry, but there is one lone pair present. Like in this case, initially we have discussed the structure of tetrahedral, the angle was 109.5 degrees. But in the case of ammonia molecule, since one lone pair is also present, so the angle reduces itself to 107.5 degrees. Now tetrahedral is the geometry. Trigonal pyramidal is the shape of the ammonia molecule. If somebody asks what is the geometry of ammonia, that means it is tetrahedral. Now, if we discard the lone pairs and then we predict the shape, then the shape is trigonal pyramidal. Same way, the shape of water molecule is bent, but the geometry is tetrahedral geometry. Since there are two lone pairs present, so there will be maximum repulsion, due to which the angle is 104.5 degrees. So this was based on 4 electron pairs. Next is that if supposing there are 5 electron pairs, but in those 5 electron pairs, if there is lone pair also present, then what are the examples? Now trigonal bipyramidal is the example of 5 bond pairs. The example we have done was PF5. Now, if supposing that has one lone pair, that is a seesaw shape, the example will be SF5. If it is T-shaped, then the example is CLF3. In CLF3, there are two lone pairs, and in linear structure of XCF2, there are three lone pairs which are on the equatorial position, and the shape of the molecule is linear. Now, based on 6 electron pairs, that's octahedral geometry where 6 bond pairs are present, the example is SF6. Now, but if one lone pair is present, then the shape becomes square pyramidal, example is BRF5. And if it is XCF4, in that case, two lone pairs are present and there are 4 bond pairs. Accordingly, the shape becomes square planar. The geometry in all cases is octahedral, but the shape changes due to presence of lone pair of electrons. So in today's class, we have studied how to predict the geometries and shape of covalent compounds. Thank you so much.